physics class.
So I do have another question. Are we done with labs?
Are you done with the labs?
Like our centripetal was the last one? I know we've got a lot to fit in for the next 2 weeks.
Yep.
Well, this week and next week.
Today, then, part of class next time, and then Tuesday. Yeah. That is quite possible. Time flies when you have fun. Or when the course is 8 weeks long. Yeah, there's one more that I would like to do, but I'm not sure how realistic that is right now.
I'll be honest with you, probably not very. It's very, we got a lot going on.
Yeah. At least I have one decent marker. All right, so let's start out with, well, I think I've killed enough time here that there's a question I wanted to ask you in terms of scheduling. Is there anyone in here who needs to complete 151 and 152 in one semester? Five. Okay. I was also asked by Mike Jones to tell you to check your email and fill out the form. They're trying to get group tutoring sessions going, so if you've not seen that email, please go looking for it. And yeah, that other question is not for your. Okay. Any questions? Yes? It primarily covers chapters 2 through 6. So after you've done the second test, it makes sense to do it. They're having some understanding of momentum and energy might help you look at some of the problems a little bit differently, which might help. But if you thoroughly understand 2 through 6, you should do fine. Other questions? All right. And I guess we're filming now. Multiple choice test is on Thursday by popular demand. And it's possible the centripetal motion lab is the last lab.
What about test correction?
Oh, I'll be handing tests back today.
Okay.
So you'll have a chance to do test corrections before the end.
And I imagine there probably won't be test corrections for the multiple choice.
No.
Okay.
Or the last one.
Or the last test.
Or the last.
I have found that my grading's a little bit more lenient on the last test because I know there won't be test corrections. Any other questions? concerning administration or content? All right. I want to go through at least one perfectly elastic collision problem. I think the videos are out there, so presumably you've seen them. So 5 kilogram mass going at 4 meters per second to the right. 2 kilogram mass going at 3 meters per second to the left. They will collide. In a perfectly elastic collision. So first off, what does perfectly elastic collision mean?
They bounce and you don't lose kinetic energy.
Okay. And the fact that they don't lose kinetic energy actually means that they'll bounce. That if they don't bounce, they will have maximum loss of kinetic energy. So there's 3 techniques that I go out, that I do in the videos. It really depends upon which one you prefer. Personally, I like technique number 3, where we shift the reference frames, but I'll be glad to do it in one of the other forms if anyone would prefer the other forms. Because I think my general advice is pick one and stick with it. Is there a form that people would rather I do? Okay. So we're basically going to shift it into a different reference frame. And for those who are not as familiar with the videos, that if I'm moving at 4 meters per second, so back up to a second, these velocities right here are based upon what we generally call the problem frame or the lab frame. In other words, we're sitting here, we somehow measured the speed of each of them, and that's how fast they're going relative to some observer. But as an observer, if I'm going 4 meters per second that way, this one will look like it's at rest to me, and this one looks like it's coming at me at 7 meters a second. So if that's the case, then the total momentum changes, depending upon the reference frame. But momentum is still conserved regardless of the reference frame, so what I'll have to do is pick a reference frame where momentum, and then solve the problem in that one. So I'm going to pick the reference frame, what's called the zero momentum reference frame. I'm going to pick however fast I would need to go in order for my total momentum to be 0. So doing it out the slightly longer way. If I'm going at 4 meters per second, then I would just subtract 4 from that, and I'd have 0 and -7. If I'm going at 3 meters per second that way, in other words, my velocity is -3, I would subtract -3, and so this one would be looking like it's going at 7 meters per second towards me, and that one would be at rest. So however fast I'm going, I just subtract it from there. So my momentum here is mass times the velocity that it will appear to me, where v is my personal velocity. I'm going to establish to the right is positive, plus 2 times -3 minus v is equal to 0. Because I want to pick out how fast do I need to go so my total momentum is 0. And again, this is mass 1, velocity 1, plus mass 2, velocity 2. Is equal to my total momentum. And it's just a matter of solving for v. 20 minus 5v minus 6 minus 2v is equal to 0. -7v is 14 minus 7b equals 0. D is equal to 2. Unless I made a careless error. We can double check that. Because the zero momentum frame is also the velocity to get to the zero momentum frame is also the velocity of the perfectly inelastic collision. So let's just do that one real quick. Perfectly inelastic collision.
The two stick together when they collide.
Absolutely. Which means their final velocities have to be the same because they're stuck together. So perfectly inelastic collision, I have 5 times 4 plus 2 times 3, so this is the total momentum in the original frame, is equal to 7 times whatever the final velocity is. Oh, that should be negative 3. So I get 20 minus 6 is equal to 7 V final. 14 is equal to 7 V final. V final is equal to positive 2 meters per second. So typically on the last test, I'm going to give you the situation, set it up, and then to say how fast are they going. If it's a perfectly inelastic collision. So once you have that answer, you've basically done that initial part over there for the perfectly elastic collision.
Can you explain how you got the 7 again?
Because they stick together, they're now, I'm considering them one mass.
Oh, okay.
And so 5 kilograms plus 2 kilograms. The other questions up to here. All right. So I'm now working in this new reference frame here where I'm going at 2 meters per second. As an observer, that's how fast I'm going. So this will look to me like it's going how fast? I saw the gesture, which I assume was not intended to be an obscene gesture, and then I heard someone say it very quietly, 2, because 4 minus 2 is 2. And what will its velocity be?
-5 meters per second.
Yes. -3 minus 2. So this is the problem I'm now working in. Got a 5 kilogram mass here, going at 2 meters per second to the right. And then this 2 kilogram mass going at 5 meters per second to the left. I hope you can see that the total momentum is 0 there. 5 times 2 plus 2 times -5 gets you 0. When they collide, they will bounce, as Olivia said. My total momentum is still 0. My kinetic energy is conserved. So if my velocities just change signs, then that means the speeds haven't changed, so my kinetic energy is the same. The total is still 0. So this one's going back at 2 meters per second to the left. This one's going to the right at 5 meters per second to the right. So hopefully you can see the total momentum is the same, just this time it's 5 times -2 plus 2 times 2 times +5. And kinetic energy is the same because the speeds are the same for each mass. But to finish it, I need to get back into my original reference frame. I can't just leave it there. Well, I subtracted 2 to get out of this frame, to get over to here, so I'm going to add 2. So what is my total momentum now? Sorry, try that one again. What is my velocity in the 5 kilogram mass?
Zero?
Negative, well, or nothing. No, yeah, 0.
There, yeah, 0. So it actually stops. And my 2 kilogram mass?
7.
Let's find out if we made a mistake. So we're going to look at kinetic energy. Because we start out with 14 units of momentum. I think we can clearly see we have 14 units of momentum here, so momentum is conserved. Dylan?
How do we get the 5 again? The 5 meters per second, 2 meters and 5.
This right here. In this particular technique, this technique number 3 to solve a perfectly elastic collision, that if I'm in the zero momentum frame after they collide, and if no kinetic energy is lost, they'll collide and basically their velocities will switch signs.
Okay.
And so since this was coming at negative 5 meters per second before the collision, positive 5 after the collision.
So this is an entirely different problem from that one, right?
No, well, we did this in order to figure out how much we needed to subtract from each of these.
Okay. Did that answer your question?
Yeah.
Okay. I got you.
So is that kind of like the balls hitting each other? Like they equal, like Newton's third law, kind of?
Yeah, it actually stems from that, well, that's the whole idea of conservation of momentum, is that when they collide, they hit each other with the same magnitude of force, just opposite directions, for the same amount of time. So momentum is, in a closed system, momentum will be transferred from one to the other. You know, ultimately, you can connect almost everything back to Newton's second or third law. So, I don't know if it helped you or not, but yes, we can connect it back to that.
Okay.
Other questions before we check to see if we made a mistake?
The +2 came from the velocity that we found. Where?
All right, so we started out with our 2 velocities. I was going to do this at the end, but I'll do this now. So I have a 5 kilogram mass and a 2 kilogram mass. My initial velocities, so this is the lab frame, are 4 meters per second and negative 3 meters per second. This is before the collision. I shifted it to the zero momentum frame. So to shift to zero momentum. The fact that I got 2 right here tells me what I need to subtract from each one. So I'm basically going to subtract 2. So this gives me my initial velocity in the zero momentum frame. So that's 2 and negative 5. Then there's the collision. However you wish to decorate it.
Beautiful.
We're going to flip the signs now, so it's negative 2, so this is my final velocities, and positive 5, again, in the zero momentum frame. And now I need to shift it back to the lab frame. Well, I subtracted 2 to get out of it, I have to add 2 to get into it. So that +2 is because it's the opposite of what I did here.
Got it. Okay.
You got a hand up, Daniel?
Yeah, so unless it's stated in the problem that the reference point is still, we should do that step every time.
Reword that?
On any perfectly elastic collision problem, do we do that as our first step?
If you're doing this technique, yes.
Okay.
But recognize this first step here is the same as solving the perfectly inelastic collision. So if I ask for this first for this problem, you've already done this.
So they're basically just the same kind of
Yeah, and it's not kind of, it is the same, the exact same thing.
Yeah.
It will always, for the perfectly one-dimensional, again, one-dimensional perfectly elastic collision, figuring out how fast the observer needs to go in order to get to the zero minimum frame will always be the same answer as solving the perfectly inelastic collision. I will amend that. In classical physics, it will always be true. Once you get to relativistic speeds, it falls apart, but that's something for the end of 152. Other questions before we? And then, so finally, my final velocity in the lab frame, or the problem frame, to get 0 meters per second and 7 meters per second. When I am coming up with the solutions, when I write the problem for the test, when I'm coming up with the solutions, this is basically what I do right here.
It's just easier.
All right, let's figure out if kinetic energy was indeed conserved. I'm about to ask that question, which all of you should know the answer to, and will answer in unison. Here we go. What's the formula for kinetic energy?
Half mv squared.
That's not too bad. So if I want to know what my total kinetic energy initial is, I got 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So what's mass 1? v1?
Oh, 4.
Mass 2?
2.
v2?